Welcome to Mobile Interconnect Threads, how next-gen products may be already outdated, in Lagoon JKL with Guillaume Tessier. Before we begin, a few brief notes. Please stop by the business hall located in the Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2. There will be mimosas there at 11:50 and an ice cream social at 3:20. The Black Hat Arsenal is in the business hall on level 2. Lunch will be available in Bayside AB from 1 to 2:30. And don't forget the merchandise store on level 2 and session recordings from Source of Knowledge. They have a desk on every level. Questions after this talk will be taken in the wrap room, Reef A. And please remember to put your phone on vibrate or turn it off to avoid interrupting the presentation. And now, please welcome Guillaume Tessier.
Hello everyone. I'm very pleased to be with you today, and it's an honor to be a speaker at Black Hat. So let me tell you, thank you for this. Today we'll be talking about mobile interconnect threads. So I would like first to make a quick overview of the presentation. I would like to start with a brief introduction to mobile interconnect, what it is, what are the threats, and what are the potential solutions that we operators bring to this. We'll dig through the SIG-to-N stack, unwinding the different layers and trying to find things that could be implemented wrongly by SS7 firewall vendors. And at the end, there will be a slide of key takeaways to highlight the most significant things that you have to take away with you. I don't know if I mentioned it, but my employer is Orange, which is a European operator with many affiliates all over the world. And this work, I work as a security researcher, and while I work on SS7 firewalls, these are not my only activities. I have other activities as a vulnerability researcher. So Interconnect 101. Let me tell you a short story. When I arrived in the US a few days ago, my mobile had a SIM card from Orange, my operator in France. And it happens that in a SIM card there is a secret, which is essential because it allows you to authenticate to the mobile network. In France, it works because the radio network is the same as the network that has the secret on my SIM card, right? Here in the US, the problem is that the US operator on which I attach to does not have the secret that is necessary to authenticate me. So what it means, as my mobile works in the US, is that there must be a link between the US operator and my home operator in France for the secret to be correctly processed and messages to be flowing correctly between the radio side here in the US and my home operator in France. What it means also is that there is a link between operator, which we will call interconnect here. There are functions that can be exposed via this interconnect, like for example roaming, international calls, international short messages. And all these functions are implemented in SS7, right? So now we know interconnect and SS7. The interconnect initially has been set up and designed between a few operators that were nationwide operators in the 80s between not that many people. So what happens at that time is that there were no security in the design protocols, in the design of SS7, which means that all the functions, roaming, international call, and SMSs, can be triggered and leveraged once you have an access to this interconnect network. For those who know, the interconnect network is something called GRX or IPX. So there was no security at the beginning, and then in the later on, 20 years later on, mobile came. And mobile came by you reusing this SS7 interconnect that was made for fixed network. As we know, mobile networks have exploded all over the world. There are multiple generations, multiple vendors, multiple whatever you want. And of course, there are also mobile virtual network operators that act on top of mobile network to resell their services. So it happens that due to the explosion of the mobile, there are many new network operators that will have access to this protected network at the beginning that is not protected anymore. And of course, what we see now is that SS7 has been used as a vector to steal some sensitive information, like for example, bank send second factor authentication to their clients using SMSs. And if, of course, you can steal this SMS using SS7, then you can access to a sensitive information. And maybe most of you know because this SS7 let's say, attacks has made their way to the meter attack framework. And there are two items related to SS7. One is to track a device location using SS7. And the other one is to redirect phone calls or short messages from a target. So this is something that we have to defend against. And GSMA pushes a way to defend against those attacks. The proposed way is to deploy a signaling firewall or equivalent. So now we know the term signaling firewall in order to protect against those threats. It has two functions. It can monitor and it can block the signaling malicious traffic. It is important because there we know that the SS7 firewall, the SS7 firewall we'll talk later in this presentation, will have two functions. It can either monitor or block the traffic, which means that it can be passive or active. You can take the interconnect, tap the interconnect, and bring the packet flow to the equipment so that it can detect malicious attacks in this flow, but not block them. Or you can put the signaling firewall online and then send messages that will stop the attack once it is detected. Okay, so now that we know about a signaling firewall, we'll go deeper into the threat model. Our main activity was about assessing the security of a signaling firewall, SS7 firewall, and to incorporate it into a new service to protect our customers and our networks. So the target of our evaluation is a security product called SS7 Firewall. We do try to protect our networks here on the right, made of HLR, MSC, all mobile network nodes that are very important to network operator. And we have traffic that is flowing through the SS7 firewall. There can be some legitimate traffic, which means that the SS7 firewall has to be resilient. It has to be protected against denial of service attack because we do want legitimate traffic to be correctly flowing through the SS7 firewall. And there are, of course, some other people that might try to attack the signaling firewall via the SIGTRAN link. SIGTRAN is, let's say for the moment, an equivalent of SS7 that we saw before, and I will dig deeper into the differences between the two just after. But in our threat model, attackers can use SIGTRAN and send arbitrary messages to the component, and we'll assess the security of those components. Of course, this component has a SIGTRAN interface, but it has also many other interfaces like SNMP, SSH, whatever GUI you want. And we'll not be talking about this one because this one are more dependent on the product or the implementation, but we'll be talking about SIGTRAN interface and SIGTRAN bugs, weaknesses, and potentially exploits. So we have our product using our SIGTRAN interface, and the question now is, what do we do to assess the security of such a component? So basically, if we have access to the component, we do not have access to the source code of the component, and we have the first task is to be able to identify the various parts of the product, libraries, binaries, configuration files, whatever, and what they do, because we want to get a focus on the signaling traffic, so we have to know where in the product is located the code that perform decoding, analysis, and verification of those messages. So we had to reverse engineer system-wise and binary-wise, get to the machine code that was running on the machine and try to find vulnerabilities in this. We have also performed some fuzzing on this equipment, either using homemade fuzzer or using some commercial fuzzer that we also have in our lab and in our society. And at the end, because we want our bugs findings and weaknesses finding to be much powerful, we do exploit development, which means that we have POCs to highlight the fact that what we have found is really something important and cannot be neglected by vendors. They have to fix it, and they have to fix it correctly, because it's something that can be used by attackers to gain remote code execution on the equipment. At the end, the cool thing is that we end up developing a tool that is not yet released, but will be in a few days. I cross my fingers, which is called Pawn SS7, which allows you to modify and to generate packets that will be processed by the SIGTRAN stack of the SS7 firewall. And we're able to successfully write several proof of concept and exploit to make it crash or to run arbitrary code on the SS7 firewall. As I told you before, there's a slight distinction between SIGTRAN and SS7. SIGTRAN is for packet networks, whereas SS7 was more for TDM networks. The difference here is between the phi layers at the very bottom of the slide. SIGTRAN is just the transport of applicative SS7 legacy protocols like MAP, like TCAP, like SCCP, just as with the SS7 on top of IP networks. And in between, there were 3 layers that were added. Of course, IP, because we are talking about packet IP networks. SCTP, because it's a specialized transport that is made for telco needs like multi-hosting or several things like this. And there is an adaptation layer that roughly takes the MTP, all the MTP parameters that you can have, and that put them in the adaptation layer. So the SIGTRAN stack is the one on the right of the slide. And we'll now be digging into the different layers of this stack. So first, from the bottom, we have IP and SCTP. These are IETF standardized protocols. And as these are low-level protocols, the thing is that they are, let's say, hardwired somehow. The format, the length, and the different fields that you can find in such protocols are very strict. And we have dig into this, but we have not found a lot of things yet. Of course, if the SS7 firewall is to be used in a passive way, then you know that we might find some things, because then the IP and the SCTP is to be done by the component itself and not by the Linux stack. So we expect the SS7 firewall to be able to at least do this verification and processing. First, it has to check source and destination addresses, and there's nothing to say there because this was correctly done, and you can block IP that you don't want to interact with you. Nothing we have found there. But you have 2 things that are very interesting. You have to reassemble IP fragment, because IP allows to use fragmentation, and also SCTP does the same using segmentation, right? And so these were functions that we are testing, and while we have not found very interesting bugs in there, like memory corruption or so on, we have found that it's a very convenient way to bypass detection from the SS7 firewall. At the IP level, there is a pseudocode here that I wrote that shows that when the SS7 firewall processes an IP packet, it just tests if it is a fragment or not. If it's a fragment, as reassembly has not been implemented correctly or at all in the component, it just discards the packet, and it is not able to detect it as an attack because it just does not perform the reassembly. So using IP fragment is a good way to evade detection by the SS7 firewall, or at least it was, because now it's fixed. And there's also SCTP. So this one is a little bit less obvious, but using SCTP, you can also perform segmentation. And of course, if you receive segmented packets, then you have to reassemble them before going deeper, analyzing at the upper layers of the protocols. And this shows that if there is a chunk type data chunk, it won't do anything. Particularly, it won't verify any of the fields that are used in the reassembly process, which means that if you send a segment using SCTP, the result is that the TCAP layer will try to analyze it, and it will fail because it's just a portion of a regular packet, and it will drop the packet, and when dropping the packet, it will say, okay, let it go because I can't analyze this, so let it go. And of course, at the very end, at the very far end of the communication chain, the equipment that will receive these fragments or these segments will be able to reassemble them, and they will have their malicious effect. So it's a good way to evade detection. Next, now that we have seen SCTP and IP, we will not go over M3 UA because there was nothing very interesting to say there. And we'll move on to SCCP. SCCP, as you know, and as I've seen you at the beginning, is a legacy SS7 protocol. So from now, what I will be talking about may be applicable to some SS7 products or world also. SCCP was built on top of MTP to extend MTP routing, because MTP is a routing system that is only based on point code. And using SCCP, you had more information like subsystem number, and global title that can be used to route messages smartly. A global title, for those who don't know, is simply a phone number, and this is how nodes in a mobile network are addressed, using their mobile phone number like every other mobile phone number. And of course, as we talk about IP, SCTP, fragmentation and segmentation issues, there is the same at SCCP level. Why, you could ask? Because in the legacy SS7 stack, the way to send big message was to fragment them, and this fragmentation process was implemented at the SCCP level. So now, back to Cictron, we have 3 layers where we could perform segmentation. It's IP, SCTP, and SCCP2. Tasks that we expect from an SS7 firewall is to retrieve the cold and caller addresses to be able to verify that the global titles have the right to communicate at the SCCP level and potentially block global titles that are known to produce bad traffic. And next, we also want to assess the fragmentation and the reassembly that is performed at SCCP using XUDT fragments. So let's go on. Before being able to retrieve the caller and the callee addresses, you have to first parse the message. And here is an example of a SCCP message. There is a very strange thing here that are called forward pointer. In the message, you have bytes that will be used to offset other part of the message, right? The arrows on the left of the block. And this is something that is kind of weird, and is something that people can get implemented wrong. And perhaps you guess it, but of course people implement it wrong in some cases. This is a kind of UDT message, and the code is retrieved using the offset SCCP square bracket 2. And this way, you can see that there are absolutely no verification that are performed. So we can basically make the cold pointer point outside of the SCCP received message. Here, the SCCP square bracket 2 is only an octet, which means that we have at most from 0 to 256 bytes of displacement. So we cannot make anything of this. But using another type of SCCP message, which is called LUDT, then the length is not on a single byte, but now the length is on 2 bytes, which means that from 0 to 256, we have moved to 0 to something like 65536 bytes of displacement, which means that now we can access to some memory area that we are not allowed to access and cause a denial of service by crashing the process this time. Okay, so now let's move on. We'll be talking about the caller and called addresses. You remember that we talk about point codes, subsystem numbers, and global titles. These are all the different extensions that were brought by SCCP. There is a way, there is a bit field in order to know what kind of information is contained into the addresses at the SCCP level. And of course, treating this bit field is a little bit difficult, and some implementations got it wrong, which means that in this case, the process UDT message will try to guess or to correctly calculate, but the calculation was not correct. And the computed GT size is negative. Why? Because of the bit fields that we have seen before, and there was a bug in the implementation. So now that the believed GT size is negative, the next point is to watch that when processing the calling and retrieving the digits of the number, this size is given as a length of a variable length array. We'll dig in the next slide to see what happens. And next, this array is filled with the digits from the message right there. What happens is that digit is allocated on the stack. Why? Because it is a stack variable, and the size is dynamic. So you can't know in advance from the quantity from which you have to subtract the stack pointer to be able to know the digits pointer. And of course, when everything works fine, size is positive, which means that you subtract a positive number from the stack, which means that digit is effectively above the rest of the stack. If you give a negative number, what happens is that digit is not, when you subtract a negative number, in fact you add something to the stack. And then digits will point not above the stack, but below the stack. And below the stack, we know that there are sensitive information like the save frame pointer or the save program counter, which will allow then an attacker to interfere with the saved values and redirect the execution flow onto interesting function that he might be able to know. We have retrieved caller and callee. We're able to filter out messages based on these values. And now we'll dig into the SCCP segmenting and reassembly. This is an extract from the ITUT document, which is a very big and maybe a little bit boring document. But in this case, implementation has strictly follow what is highlighted here in green. And they take here every XUDT message. They verify that when they concatenate the different fragments, they don't overflow the big buffer on the top, and this is fine. And once they see a message with the M bit set to 0, then after having concatenated it to the buffer, they will write it into another buffer, which is a TCAP buffer to perform TCAP decoding, the upper layer above SCCP. And there is something wrong here because the buffer initially was okay, but the destination buffer is much smaller than the big buffer that we have concatenated and reassembled the fragments into, which means that in bullet 3, we have an overflow, and we will overflow the smaller buffer. So with this, we can perform a denial of service. But there's more because the part that was hidden, in fact, is the head of a linked list, which means that by overflowing smaller buffer, we could overflow those 2 pointers here, and we could set them to arbitrary values. And when you unlink a cell from this list, and you have mangled pointers, attacker control pointers, then you can perform arbitrary write into the memory of the process. This one was in a kernel module in Linux kernel. There was no KASLR, which means that you are able to predict the addresses in the BSS section. So you're able to know exactly, you're able to first to put arbitrary content into the memory and to know the addresses that will be used. And you are also able to write wherever in the memory you want to write. So basically you can turn this into remote code execution via arbitrary write into the kernel memory. And next, we'll have a look at TCAP and MAP. I'm sorry because I'm a little bit late. TCAP and MAP are very similar because they share one thing. They are specified in ASN1 and they are encoded in bear. Usually, what you expect from ASN1 is to shield you from programming error. Why? Because usually you take the specification, you generate C code based on the specification using an ASN1 compiler, and then you generate the machine code. So if the specification is okay, and of course it is, then it will generate correct C and correct machine code. But now, the problem is that how you use ASN1 that are correct functions generated for parsing, decoding, and coding. And of course, there will be some problem in the way that you interact with those safe functions. At the TCAP level, we have to retrieve the application context name. Why? Because it allows you to correctly decode and verify the map message that is above TCAP. So the SS7 firewall has to retrieve this information. And at the map level, there are two things that are important. It's the opcode, to know the precise operation that will be done using this message. And of course, the parameters of this message, because you want to verify some parameters are correct and coherent with the other layers of the message. And the first vulnerability that we have found is that retrieving the application context name is fine, but then it will be stored in a smaller variable. Here we have only 8 bytes, whereas the length, ACN, in the message is attacker control and can be arbitrarily long, almost because there are some limits due to the way that ASN1 encodes length into bear, but anyway. So using this one, we can get a rope chain and successfully gain code execution on the equipment. The next one is very interesting too because it's a failure to understand how ASN1 works. You remember about the opcode that we talked about? It's an integer value, and to be able to process messages correctly, the implementation takes the opcode and then perform a lookup in a table in an array of function pointers. They do verify that the opcode is not bigger than the array size, and they verify also that there is something to do, meaning that the function pointer at this offset is not null. But what they fail to do is that they fail to think about the fact that ASN1 can have a signed integer, which means that, of course, the opcode will not overflow the maximum size of the array, but it can be negative and it can be as negative as the attacker wants, which means that in this case you will be peeking into memory several thousand of bytes before the map-up code, and you might be able to get a way to put some function that you want to execute and then execute the function pointer. So this way you can make an arbitrary function call into the SS7 firewall. Key takeaways. All these vulnerabilities are either IP SCTP or SS7 based. They might apply to other SS7 products. We might think about 5G making disappear those weaknesses, which is probably true, but we also have to live with legacy network because we can just disconnect them and power off. There are many services that rely on 2G or other generations. What is very bad for this product is that they have vulnerabilities and hardening measures were not implemented, let's say, at all, which means that if you find something, then you can exploit it and run code on the sensitive equipment. I believe that I'm nearly finished with my talk.